Everyone. Today I want to introduce the topic related to how to improve the user experience. When a user needs to process a English test, the driver is an influence evaluation probability minimization related to the and my next step is my partner's name. Let's start with the content. In the first part, we will introduce the main idea of this paper. Then, in the second part, we will explain some difficult terminologies about this paper, which make us easily understand the further concept. As for the third part, we will explain what the system model looks like. Then, in the fourth part, we will explain how the uploading algorithm works and how to derive the occurrence violation probability of the whole system. Finally, we will show some experiments result in this paper. So first, the part abstract. When we start the paper, what is the most important thing to know? The answer is what purpose only want to solve. Now, let me tell you the concept. When the user wants to process a large text, the user doesn't have enough computing resources to complete the task on time. In this time, the user can transfer the task to another computing resource like RAM or external compute the task. Using this way, maybe can reduce the task computing delay and meet the real-time task requirements. So the system is called federated architecture. Let's go back to the slide. Question: in a federated architecture includes user, cloud, server, VPN, or how to reduce the task violation probability of the whole system, and how to solve the problem. The idea is by setting the optimal uploading probability of each task, the fewest violation probability of the whole system can be minimized. Finally, the order of this paper presents a solution to deal with the problem. Using the two theories, get the fewest violation probability of the whole system, then adjust the uploading probability, probability, and see if we can get a better result of the fewest violation probability. The second part, terminology. What is quality of service? QoS. QoS is the network traffic management mechanism which ensures certain tasks can be finished on time. QoS is usually deployed in a large shared network, and we want to make sure some applications are still working efficiently. As to the QoS violation probability, QoS violation probability is a probability that a task cannot be finished by the required time. When a task cannot be finished by the required time interval, then we call this is the QoS violation. So the QoS violation probability is the probability of the QoS violation in the system. The third law of flow means that behavior transferring the task to another computing resource like cloud or server without ceasing. In most situations, we upload because we want to get the result as soon as possible. Then what is uploading probability? And we say the uploading probability to the cloud is 0.2. It means the 100% of the total text will be uploaded to the cloud. So how many uploading tests can we choose? Let's look at this picture. The user can upload the text to the cloud over the edge server or the vehicle block using the cloud for computers called mobile cloud computing, and using the edge server for computers called mobile edge computing. As for the vehicle for computing, what is vehicle for? If we can use the computing resources in the electric vehicle, then the electric vehicle from the computing resources box, the user can use it. And the cloud has a powerful computing ability, but is maybe not a good decision to upload all tasks to the cloud, because the cloud is further from the user, which may spend more time on transmitting the data as an alternative. Uploading the task to the edge server or the vehicle block sometimes is the better way because they are near to the user. In fact, vehicle block contains two types of block. One is called parking lot block, and the other is called traffic intersection fault. The difference between that is the vehicle in the parking lot fault will stay longer than in the traffic intersection fault. For example, the vehicle in the parking lot fault will stay 10 minutes, but the vehicle in the traffic intersection fault will stay just 1 minute. And the third part, the system model. After explaining some technologies, we take a look how the author defines the system model. So this is the system model, and the capital U is here, capital U stands for the user, and the F1, this stands for the traffic intersection, and the F2 stands for the parking lot fault, and the F2, stands for the parking lot fault. And the notation E stands for the edge server computing, and the C stands for the cloud server. So there are 1 user, 3 traffic intersection fault, 3 parking lot fault, and 1 edge server and 1 cloud server. The user can upload the task to the edge over fault, and the edge server can upload the task to the cloud. The notation lambda denotes the arrival rate of the task. It's a personal process. And notation P, this P is the uploading probability. So let's focus on an example. This PUE. The notation PUE means the user upload how much percentage of the task to the edge server. And the block and the block, it represents the array, and it is the waiting queue of the task. And as for the U, is U denotes the service rate of the task. It's a person process too, and the UU represents the service rate of the user, and the UE represents the service rate of transferring the task from user to edge. Finally, in this paper, the author defines the edge server, the cloud server, and the user are all in one model. So the fault is an ANC model. That is to say, there are more than 1 server in the mobile phone computing.
So let's first look at the probability of offloading from here is the user equipment, and offloading to the F1 and F2 and edge are PUF1, PUF2, and PUE. These 3. So the sum of these 4 probabilities should be 1 because there are all the possibility of offloading. And so let's look at how to minimize the QoS violation probability. This is QoS violation probability, and we want to minimize it by adjusting these 4 parameters. And so these 3 is between 0 and 1, the sum of these 3, because 1 minus these 3 is the force, the processing by user equipment itself, and this is the independent variable. It's from uploading from edge to the cloud computer, so it's independent to these 3. Okay, then this is the formula of QoS violation probability. So long, right? Don't worry, we'll not cover the calculation in this. We'll do it by computer. Yeah. So the algorithm of minimizing the violation probability is 2 parts. One part is the main loop, MPE, we call main probability estimation, and it will iterate so many times. And this algorithm is called subgradient optimization. And why it's called subgradient? Because we're going to go through every variable in one iteration of main loop and do some gradient, like gradient, to the variable. This is called sub-probability estimation. We're going to move the parameter a little bit and to see if the result is going to be better or worse. If it's better, then we'll choose the new point. Okay, so let's look at the algorithm of main probability estimation. We are going to use 3 points to represent the P, UE, and UF1, UF2. You can think of them as in the number line of 0 to 1, and these 3 points are separating the number line into 4 sections, and these 4 sections are the probability of each offloading, and the same as PEC. It's the C4, another number line from 0 to 1, and separating from processing by edge itself or offloading to the cloud. Okay, then we're going to estimate the probability with these 4 parameters, and then repeat and calculate the optimal solution of it until the new and old probability, the difference of them converges to a small number. Okay, so the new probability estimation is guaranteed to be less than or equal to old probability estimation, because we only choose better result to replace the previous result. So this is guaranteed, and the minimum difference for running the next iteration is difference between old probability and new probability are greater or equal to epsilon, and so the maximum of all probability is 1. Because the max probability is defined to be 1. So we are decreased every time by epsilon or larger than epsilon. So the only the most iteration it can run is 1 over epsilon. You can use some inequality and move them around so you can get the result. Okay, the next page. And the sub-probability estimation. This S is some C in the previous algorithm, and we move it a little bit. Like step is 1 over 8, and this is pretty large for probability. So we move it to the left and stay in the original point, or move to the right. And we test this through by computing those four probability and take into that very long formula. And then we can get the new estimation probability. So we are going to count 3 probability and compare them and take the smallest one to be the better. The point produced the smallest one will be the final result, and we replace the original point with the new result. And then we divide step by 2. This means the next time we looking for the probability, we move the point in the near. We move the point in the near right, and then do this until the step is less than data. So every time we divide 2, so the step divided by 2 to the case power or less than zeta, and we move the formula and take logarithm, we can get this. The process will run log base 2 of 1 over a zeta times. And so, next page. The complexity is where we have n times n n times n computer or computing resource to be perform this algorithm to estimate. And the arrival rate is lambda. Every time past arrival, we need to compute the optimal probability. So n times the iteration in the main loop and sub loop, we are going to multiply them all, so we can get it. By the way, this is not the result I mentioned in the previous page. And so this is my this is my estimation. I use big O of log 1 over zeta because 8 is a constant, so I can remove it. And times mn lambda over epsilon. It's basically multiply every term together and take big O notation. Okay, but this log 1 over zeta is smaller than 1 over zeta. So the take big O, this 1 over zeta is still the upper bound, although it's not tight, so it's still right. Okay, then let's back to the Candice part.
Okay, in the final part, we will show some experiments results from the figure. The figure shows the comparison of characterization variability in different architecture. We can see the phi is the algorithm of this paper has the best value of characterization variability. And the next comparison. This is the comparison of task average working time, and the algorithm of this paper has the best result too. Thank you.
Thank you.
So I think no question from me. That's good. You have the tight upper bound for the algorithm. I will ask some students to check it further. Okay, thank you.